Imagine for a moment you're in a chemistry lab and you're handed an unknown clear liquid. It could be an alcohol, a secondary amine, or perhaps a primary amine. You need a definitive way to tell them apart. You add a few drops of chloroform, some alcoholic potassium hydroxide, and gently warm the test tube. Suddenly, an overwhelming, foul, almost unbearable stench fills the room. Congratulations! You've just performed the Carbylamine reaction, and you've confirmed that your unknown liquid was a primary amine. But beyond the bad smell, what is actually happening at the molecular level? Let's look at the players involved. First, we have our primary amine, which we can visualize as an R group attached to an NH2 group. Then we have chloroform, one carbon atom bonded to 3 chlorines and a single hydrogen. Finally, we have potassium hydroxide, our strong base. Now, you might think the amine starts the attack, but the real magic begins when the hydroxide ions from our base go after the chloroform. Notice how the 3 chlorine atoms are highly electronegative. They're pulling electron density away from the central carbon. This makes the lone hydrogen on the chloroform surprisingly acidic. As you can see in this animation, the hydroxide base plucks that hydrogen right off. This leaves us with a negatively charged carbon, which then kicks out a chloride ion to regain stability. What's left is a highly reactive neutral species called dichlorocarbene. Picture this, a carbon atom with only 6 electrons and a lone pair. It is desperate for electrons, making it a powerful electrophile. This is the key insight. The Carbylamine reaction isn't just a simple substitution, it's a dance facilitated by this hungry carbene. Our primary amine, with its lone pair on the nitrogen, sees this electron-deficient carbene and attacks. Watch what happens to the structure. The nitrogen and carbon bond together, but the molecule is now messy and unstable. Through a series of proton shifts and the elimination of the remaining 2 chlorine atoms, thanks again to our base, the KOH, a triple bond forms between the nitrogen and the carbon. The result? An isocyanide, also known as a carbylamine. RNC. That triple bond is unique because the nitrogen carries a formal positive charge and the carbon carries a formal negative charge. It's this specific, high-energy arrangement that produces that characteristic, pungent odor. But here is the catch, and it's why this reaction is such a famous diagnostic tool. If you try this with a secondary or tertiary amine, nothing happens. Why? Because those amines don't have enough hydrogen atoms on the nitrogen to be eliminated during the process. Without those 2 hydrogens to give up, the stable isocyanide triple bond can never form. So the next time you hear about the Carbylamine reaction, don't just think of it as a smelly test. Think of it as a masterclass in organic carbene, which then forces a primary amine to transform its very identity. It's a reminder that in chemistry, the most dramatic changes often come from the most unstable intermediates.